Chapter 3, Alkenes and Alkynes. We'll begin with some general properties of alkenes and alkynes. Alkynes contain a triple bond, and alkenes contain a double bond. Now, both compounds are hydrocarbons containing only carbon and hydrogen atoms. So a double bond consists of one sigma and one pi bond, and a triple bond consists of one sigma and two pi bonds. Both types of compounds are considered unsaturated as they contain pi bonds, and they are also known as olefins. Here are the general equations for alkanes, alkenes, and alkynes. So as I've stated already in Chapter 2, alkanes follow CN H2N plus 2. Alkenes follow CN 2N, and alkynes follow CN 2N minus 2. So every pi bond results in the loss of a pair of hydrogen atoms. In a molecule containing multiple double bonds, the arrangement is important. There can be three types: accumulated, conjugated, or isolated, which are non-conjugated. So conjugated are especially important as the pi bonds can interact. Accumulated double bonds are simply double bonds next to each other within a molecule. Conjugated, note, have one space, so there's a single bond in between the double bonds. And isolated double bonds have more than one space, right? More than one carbon-carbon bond between them. This is important later on for certain types of reactivity. So bonding in alkenes. They're sp2 hybridized. They're trigonal planar, and the bond angle here is of 120 degrees. There are 3 sigma and 1 pi bonds, or 2 single and 1 double bonds. The CC double bond is about 1.34 angstroms, so it's a little shorter than a CC single bond. And this is very important, that the pi bond locks the geometry to planar. So in alkenes, we lose the ability to rotate about that carbon-carbon bond. And here's a representation of the orbitals. So the sigma bond is made up of an sp2s to the hydrogen, and between carbons it's an sp2sp2 sigma bond. And the pi bond is simply an overlap of 2 p orbitals. In terms of the geometry about a double bond, we describe it as cis or trans, meaning substituents can be on the same side or opposite sides of the double bond. And that influences the reactivity and also the physical properties of a molecule. So let's look at dichloroethylene. Cis 1,2 dichloroethene has a boiling point of 60 degrees. The trans 1,2 dichloroethene has a boiling point of 47. And this is arising from a difference in the dipole moments about the molecules. As I've said, the double bond removes the ability for rotation about the carbon-carbon bond. And under most circumstances, it will not interconvert between cis and trans. If you have light or heat energy, it is possible to interconvert the two isomers. In the following reaction sequence, we see cis dichloroethene forming a radical. That radical then is a single bond about that carbon-carbon, and it can rotate and then regenerate the double bond. So let's talk about the chemical reactivity of alkenes. They are more reactive than alkanes, and this arises from the double bond. The pi electrons, okay, the pi bond it's weaker than the sigma bond, and these electrons will react first and will react through what are called addition reactions. So if you look at the general scheme here, we have a double bond reacting with molecule AB, where A and B will add to the double bond, and the result is a molecule with only a single bond. We call this an electrophilic addition mechanism, and it's very important. Mechanisms are the way that organic chemists describe the mode or steps of forming a product from a reactant. So the basic mechanism is the same for all the reagents. It's a two-step mechanism where an electrophile, a species seeking electrons, will add to the pi bond in the first step. And this creates a species called a carbocation. So that's going to be an intermediate species with a positive charge. The second part of the reaction involves a nucleophile, right? A species seeking the nucleus. That adds to the carbocation in the second step of the reaction. So here we have our nucleophile. The double bond, the pi electrons, will seek out the electrophile because it's partially positive, liberating the nucleophile. This creates an intermediate of a carbocation, a species with a positive charge. The nucleophile will then add to that carbocation. So let's talk a little bit more about carbocations because they're an important intermediate in several types of organic reactions. They're an electron deficient and have an empty p orbital. So with that, the geometry then of the substituents will be 120 degrees about that vacant p orbital. And just as we had a ranking of stability of radicals, we also have a ranking in stability of carbocations. The most stable is a tertiary. The intermediate is a secondary, and the least stable is a primary or a methyl. Now, there are two modes which will stabilize a carbocation. The first is through inductive electron donation, and this occurs when you have methyl or other alkyl groups attached to the carbocation, as seen in number 1 here. Okay, we have, in this case, two methyls donating electron density to that carbocation to stabilize it. The second type of stabilization is called hyperconjugation, and this is an orbital interaction between the vacant p orbital, which is our positive charge, and a neighboring CH bond to help minimize or stabilize that charge. Another important factor for carbocations is resonance. And resonance is a stabilization by the actual donation of an adjacent pi system towards that charge. And this lowers the energy by spreading the charge over more atoms. This is a very, very common example, the allyl cation. This group right here is the allyl group where you have a double bond adjacent to a positive charge and 3 carbons like that. So by resonance, we can move this double bond over to stabilize this charge, and then the positive charge will result on or reside on the left-handed carbon in this manner. Now, to add a little complexity here, carbocations can rearrange. That is, the charge can move to an area of the molecule which has more carbon substituents. This is called a rearrangement. They're susceptible to 1,2 hydride shifts, that is where a hydrogen will exchange for the positive charge. So let's look at this. We've got a secondary carbocation here with an adjacent hydrogen. That hydrogen can move over and fulfill that positive charge, but now the positive charge will be on this carbon, which is bonded to 3 carbons. So we've created a tertiary carbocation that's increased stability over a secondary. So there is also a possibility for this phenomenon to occur with methyl groups, and that's called a methyl shift. And it's also seen in the allylic system, which was on the previous side, or a benzylic system. Now, a benzylic system is something that you should be aware of. It's an aromatic ring with a CH2 adjacent. And if you have a charge on that CH2, that charge can be spread out or delocalized throughout the ring. And that's very important in terms of reactivity. So we can add a halogen across a double bond. to produce a 1,2-dihalide alkane. And this is an important reaction. It's also a test in qualitative organic analysis in terms of unknown identification. So if a student has an unknown with a double bond and they add a bromine solution, it will go immediately from red to clear. The bromine reacts instantaneously to add across that double bond because Br2 is a reddish solution and the alkyl dibromide is going to be clear. So if we want to add bromine to a molecule of ethene, it's symmetric. Regardless of which way it adds, we'll get the same product. Now if it's an unsymmetric alkene, as depicted down here, where these would be H's and we've got an R group and an unsymmetrical reagent, it can add in this manner or it can add in this manner relative to the R group. You see in this case the X is bonded to the same carbon as the R, and in the other case the Y is added to the carbon with the R. So how can we define this and clarify this? Well, we can use Markovnikov's rule. Okay, there's a simple way to predict this. And Markovnikov's rule states that when an unsymmetrical reagent adds to a double bond, the electrophilic part of the reagent adds to the carbon with the most hydrogens on it. The mode of addition will always produce the most stable carbocation intermediate. So let's look at this. This is propene. 1, 2, 3 carbons with a double bond. It's propene. So the electrophile is H+. The double bond, the pi electrons will create a bond with that H+. And depending on which end opens up, we can form a species with the H on the second carbon, or we can form a species with the H on the first carbon. The first carbon is called anti-Markovnikov. The secondary carbon, carbocation, is Markovnikov product. So this creates a more stable carbocation. So given a choice, the electrophile will add in a manner to result in the most stable carbocation. Let's talk about hydration across a double bond. This is the reaction of the addition of water across a double bond to produce an alcohol. Now, you cannot simply take an alkene and mix it with water and create an alcohol. It requires an acid catalyst to produce the electrophile. So here are the steps involved in this reaction. The first step is the protonation of the alkene in a Markovnikov orientation. So what does that mean? The electrophile will add in a manner to result in the most stable carbocation. In this case, it's a secondary. The second step is attack of the nucleophilic water molecule right here. And then the final step is removal of a proton to form the hydroxyl group, resulting in our alcohol. Another type of reaction with alkenes is called hydrohalogenation. And don't be confused or misled by the title. Hydro in this case means hydrogen and not water. It is not hydro as in water. So we're going to add an HX, which it could be HCl or HBr or HI across a double bond to produce the Markovnikov halide reaction. And the order of reactivity is important based on the halide that's used. HI is faster than HBr. It's faster than HCl, which is faster than HF. And this parallels the acidity of these acids. And here's what occurs. In the first step, the double bond, the pi electrons will attach to the proton and create the most stable carbocation according to Markovnikov's rule. That carbocation will then be reacted or attacked rather by the nucleophilic halide species. In this case on the slide we see Br-, and that results in 2-bromopropane.